Hi, I'm George Levin, co-founder and chief business officer at AlgoX2, a data streaming operating system. In this podcast series, I'm talking with Alexei, our CEO and the creator of AlgoX2, and my goal is to understand what we're building and what's the thinking behind it. Hi, Alexei.
How you doing?
I'm good. So let's start with some details. I know that we often, when I pitch AlgoX2 to the clients, one of the topics is that we separate compute, storage, and network. Could you explain why is it important and what's so special about this three-layer architecture?
In AlgoX2, we have three main layers that you might describe, right? One is the external one where external connections come in. So producers and consumers connect to a layer of gateways. And that's your interface to the outside world. And then internally, we have these things called sequences, which turn multitudes of racing streams of messages into ordered rivers. This data eventually ends up on disks, on multiple disks, which is your storage subsystem. Along every hop of the way, from a producer to a consumer, through gateway, sequencer, commit, gateway, and out, there is networking. So every hop could be changing a host. You could be going from machine A to machine B. We don't have a kind of traditional vertical architecture where you're talking to some server that does things for you. You're talking to kind of a small node in the network, which takes your message and just sends it along, usually on multiple paths and onto multiple other servers. Because everything is a collection of such nodes, you could independently scale the number of commits, the number of gateways, the number of sequencers. Why would you scale them? Well, because they have different throughputs on their own. Sequencers are very fast. They do nothing but mem copy, essentially. Commits could be fast or slow, depending on the types of disks you have, but generally they're slow, because they're also indexing things on disk. They're doing deep indexing. The disks are not as fast as network, etc. Then you have the gateways. Are they fast? Yeah, kind of fast, but also you have TCP, you have retransmissions, you have you have many clients connecting to some gateway. You kind of don't know ahead of time how many of each component you want to have. Also depends on the deployment. You could have few producers, so it doesn't make sense to give them hundreds of gateways. You could have many producers, etc. It's very, very helpful to be able to independently scale these multiple layers, and that's what's called a decoupled architecture, where storage and compute is decoupled. And when you run additional processes on our cluster, like filtering processes or transformation processes, things that create iceberg tables or upload something or filter it, you get an additional layer that you also have to scale. And you, depending on how fast each of those processes are, you're going to create more or less of them. It's generally kind of a holy grail in systems architecture to be able to scale different layers independendly. And that's one of our design principles, is that we try to have that.
And is it right that in Kafka, when you scale it through brokers? So each broker has both compute and storage, so you can't scale it independently. If you just run out of disk, you can't add just disk. You need to add another broker which has both, right?
I would call Kafka essentially a scale-up architecture. So it's really a number of single-host, high-functionality brokers. Each broker hosts servers, so it accepts network connections from producers and to consumers. So it's the same process that does it, multiple threads, but it's the same process. And also this process is writing things to disk. So it fits very nicely within a single operating system. Now, what the process also does is it talks to replicas to make sure that your data is replicated before it's served out. But conceptually, it's very easy to think of Kafka as essentially a single process system. There's a broker, you send it a message, it saves it. Once it's saved, it publishes it out. You could view it as being vertical. It's called vertical scaling, meaning if you give it a faster machine, it's going to scale. It's meaningless to talk about a single broker using 10 machines. It always sits within one. So this was scale-up architecture. In a scale-out architecture, you don't have anything like that. You have a bag of processes, 200 gateways, 40 sequencers, 200 commits. they're all running on some servers. Well, usually it's going to be pretty uniform across servers. So you may have like 8 commits running on a server, 4 gateways running on a server, a couple sequences running on a server. But when you're talking to a server, you send it a packet. It's not getting meaningfully processed on that server. It's getting multicast out to 2 other servers. Something happens there, then it gets multicast somewhere else. Something happens there. Then eventually, maybe it goes to a consumer if the consumer is connected. If not, it goes somewhere else. So you're really talking to a data network more than a single application. So that's a very different architecture.
Let's talk now about multicast, something that creates a lot of problem for me personally, because whenever I mention that we're using multicast to our clients, it immediately creates so many weird questions and concerns. They all start talking that it's lossy, that they don't want to deal with it. Everyone loves InfiniBand as a concept, but nobody likes to deal with it. So how can we address this concern that we use multicast a lot?
Look, in the end, we're just going to address it through showing performance numbers. Okay. There's really, my love for multicast goes back at least 20 years, actually more. And when I did high frequency trading, when you do that, you connect to exchanges. Exchanges send out market data. Market data always comes out in the form of multicast. So let's say you have a data center in location 1, and there's some multicast market data coming out. And then you also have trading in data center 2. If you have a network between these 2 data centers, which you do, then you can route the multicast data so that market data goes from data center 1 to data center 2 and is interpreted there by your process. There's really no faster middleware than a network switch. Okay? So that's a very fundamental fact to realize. And a network switch will happily clone any incoming data to 10 output ports, like before you can say a nanosecond. It is extremely fast. Well, it won't clone it in a nanosecond, but it will clone it faster than you can say nanosecond, okay? It's extremely fast. It is fundamentally a form of middleware, the network switch itself. And all other middleware that we mere software engineers build are going to be reduced versions of what a network switch is capable of. And so the best you can give your clients is some sort of programmable, lossless network switch in terms of throughput. You can't do faster than that, for sure, but you can do millions of times slower than that, which a lot of people have achieved. So our goal is to be somewhere in between. We want to give the users of our platform essentially the power of that network switch. Let me just describe it, why it is so important to use multicast. And I've used it in all my systems that I've built. And we're using it in AlgoX2. Let's say you have a data streaming platform which is receiving, it's using 100 gig networking. And so you're feeding it a 100 gig stream, just for the sake of argument. If you have 10 consumers and 1 producer, here's what's going to happen. The broker or whatever is receiving that 100 gig stream will have to clone it 10 times, 1 for each consumer, and send it. But because the consumers are all sharing this single output line from that broker, they're together limited to consuming 100 gig per second, which means every one of them is consuming only 10 gigs per second. So if you want to stay real time, now the producer is only limited to 10 gigs per second. And so that's called a blocking architecture. So blocking architecture is where a single node cannot sustain the capacity, the maximum capacity of the system. The fraction of the load that's given to a single node is higher than that node's capacity, and the node starts blocking. So that's a blocking. Now, if you're using multicast, then you can have that internally, you can have that broker broadcast the data that's going to hit 10 different servers, each of which is running an output gateway, and the data will be sent out to the clients, and now you've achieved 100 gig in and 100 gigs out 10 times. So it's a terabit of data coming out. Now, the numbers are theoretical. You're not going to achieve line rate 100 gig on a 100 gig network, but the argument still stands. The only way to extract maximum performance out of a system like this is to use hardware replication.
Yeah, but I guess it's important to explain to everyone who's listening to us right now and thinking, should I know how how to use InfiniBand and Multicast, that it's an internal part of the system that we solve the problem. It's not them who need to run it, right?
That's the nice thing is that's why we call it a streaming operating system, is that it should not be your problem. If it's your problem, then you're taking the weight of the world upon your shoulders, which you should not do. In the same way that you and I don't think about how PCI Express works, it just solves problems.
I definitely don't think about it.
You should not. In the same way, the users of our data streaming platform, they should not be concerned with what tricks we'll use to get their data served faster. On the outside, it's just a familiar protocol, right? And on the inside, what do? We probe the hardware that we're running on, and if it's capable of doing certain things, then we have drivers to take advantage of that. And that's a property of an operating system. Having drivers for specialized hardware and taking advantage of hardware accelerators while keeping a user-friendly API that's unchanged and having a generic sort of software path available, that's a property of an operating system.
Let's discuss another topic that comes up very often on the clients meeting, the problem of fat topics, especially when we talk with trading firms. That's something we need to explain a lot on how we address it. Could you tell me more about it?
So first of all, what is a problem of fat topics? That's essentially a problem where you have more than 10 topics. Okay. What happens is this: in a sort of classic standard old version 1 data streaming platform design, for every subject that's published by a producer, you get something like 4 files in the system being written. Because it's saved in 2 locations, that's 2 files, and because there's a file with messages and a file that's an index, that's another factor of 2, so you get 4. If we're talking nothing is not partitioned, right? So every topic is going to be partitioned into, let's say, 10 subtopics, or they call topic partitions. So the external data comes in, it goes onto one of the 10 topic partitions, and each one of those gets written into 4 files. Those files have to be open in the OS sense of being open file. And so you get a single topic produces 40 files in a running cluster. Now, if you have 1,000 topics, then that's like 40,000 files. Then you start running into problems. Actually, you start running into problems much sooner. If you append to many small files given machine, you've essentially turned your disk access pattern into random access. And so no disk is, whether it's an SSD, regular spinning disk, NVMe, it's not going to be fast on that random access. It's going to, under sustained load, it's going to give you some terrible performance eventually. That's an issue. And a second issue is that the OS there's a lot of overhead involved just maintaining those files being open in the OS. You have FD limits being hit. You have to do a lot of tweaking to get that to work. So the way we solve that is that we say the number of files written in an X2 cluster is going to be independent of the number of subjects produced by users. Essentially, we write fat, in a different sense fat, we write these kind of aggregated append-only files, and then we produce some deep indexing using log-structured merge trees. That's an approach that seems to work well at reducing the number of open files and keeping performance largely independent of the number of topics.
Does it mean that we can do context filtering for our users, that we can filter, create kind of like virtual streams based on the context of the data we stream?
That's a different issue, right? So I guess maybe I misunderstood the fat topics. First issue is when you have lots of topics. The second issue is when your topics contain a lot of information and it needs to be filtered out at the edge. Look, there are several approaches to this. One of the things that we allow is to run sub-processes in an X2 cluster that are essentially producers and consumers. So they will read internal data, they get it at nanosecond speeds, so because they use the same delivery mechanism as the system itself is using, and they can produce filtered outputs or write additional streams, reformat things for the gateway when serving. So you could be serving a different protocol, or binary versus you could translate ASCII to EBCDIC format or something like that. We allow those sidecar processes because it's a very large and useful class of things to do. And certainly there are creative ways in which you could solve the problem of filtering down the so-called fat streams by adding a sidecar to the gateway. I guess the answer is yes, with some design considerations for the user. It's certainly easier than spawning another cluster that's going to read the data from your cluster and then producing some filtering.
I think this will be enough for our second episode. Thanks a lot for your time, and subscribe. Stay tuned. There will be more episodes.
My pleasure.
Bye.